The story of the Flak 88 begins in the interwar years, when German military planners faced a rapidly changing battlefield and a pressing need to defend the Reich's airspace against new, long-range bombers. In the early 1930s, the German arms industry and military engineering branches embarked on designing a heavy anti-aircraft gun that could reach greater altitudes, deliver precise fire, and survive sustained use. The result was the 8.8 centimeter Flugabwehrkanone, commonly known as the 88. From its inception, the Flak 88 was shaped by three interlinked design imperatives: range, velocity, and durability. Engineers deliberately prioritized a long, well-rifled barrel capable of generating high muzzle velocities and a carriage that could provide stability for sustained fire. This was not a gun built for novelty. Its engineering ethos emphasized reliability, maintainability, and the ability to be upgraded. The Flak 18, the initial production model, set the template: an 88mm caliber barrel mounted on a cruciform carriage that allowed a wide traverse and high elevation. The cruciform base granted exceptional stability for both anti-aircraft work and, as would be discovered later, ground engagements. The breech, recoil system, and barrel metallurgy were designed to withstand continuous high-pressure firing, enabling the gun to generate velocities and kinetic energy beyond what many contemporary weapons could sustain. German doctrine invested in producing not just a weapon, but a system: sights, directors, and dedicated crews trained to coordinate fire. This systems approach meant the Flak 88 would remain useful even when battlefield requirements shifted. An often overlooked but critical element of the original design philosophy was modularity. Engineers and ordnance officers designed the Flak 88 with upgrade pathways in mind. Improvements to carriages, recoil systems, sights, and barrel lengths could be incorporated without redesigning the entire weapon. That flexibility allowed the Flak 36, Flak 37, and later Flak 41 variants to evolve as demands changed. The designers intended the gun to be future-proof, capable of adaptation as adversaries increased armor thickness, aircraft performance advanced, or logistics demanded lighter, more mobile solutions. The Flak 88's industrial pedigree also mattered. Germany had a strong tradition of precision engineering, and that excellence translated into tight tolerances, high-quality steel, and well-fitted mechanisms. This attention to mechanical detail reduced fouling, increased service intervals, and meant the gun could be relied upon in harsh conditions, from dusty deserts to extreme Russian winters. The design ethos included human factors engineering. Crew positions, loaders access, and sighting mechanisms were arranged to facilitate high rates of fire without exhausting the crew prematurely. Crucially, the initial design did not envision the Flak 88 as predominantly an anti-tank weapon. Instead, the weapon's ability to destroy armor was an emergent property of choices made for anti-aircraft effectiveness: a long, powerful barrel and a heavy projectile fired at high speed. Once the weapon saw battlefield use, commanders quickly recognized that those same qualities made the 88 devastating against armored vehicles. That observation would reframe its tactical employment and elevate the weapon from a specialized air defense piece to a versatile, multi-role centerpiece of German artillery. The Flak 88's origins, therefore, are a study in foresight and adaptable engineering. Design choices intended to dominate the skies inadvertently produced one of the deadliest ground weapons of the war. At the core of the Flak 88's lethal reputation is a straightforward physical truth: kinetic energy kills armor. The 88's long rifled barrel, robust breech, and powerful propellant charges produced muzzle velocities commonly ranging from about 800 up to 1,000 meters per second, depending on ammunition and variant. That velocity, coupled with an 88mm projectile mass, generated tremendous kinetic energy, enough to pierce the armor of almost any early and mid-war tank at practical combat ranges. Unlike many anti-tank solutions that relied on shaped charges or proximity detonation, the Flak 88 used sheer kinetic force to punch through steel, a method that was brutally effective against the metallurgy and armor designs of the 1930s and early 1940s. The gun's penetration capability was reinforced by the variety and evolution of its ammunition. Initially, high explosive and fragmentation rounds were expected as primary loads for anti-aircraft work. However, the Germans quickly developed armor-piercing AP and armor-piercing capped APC rounds, designed to concentrate the projectile's force on a smaller area and to counter sloped armor. Capped rounds helped maintain projectile integrity when striking angled plates, critical when facing designs like the French Char B1 or later the Soviet T-34. The combination of high velocity and improved projectile design meant the Flak 88 could defeat sloped or hardened armor at ranges where the enemy's guns could not reach back effectively. Several operational examples highlight the destructive physics. In the 1940 Battle of France, Matilda II and Char B1 tanks, both heavy for their time, were vulnerable to 88mm hits at distances far beyond the effective range of their main guns. Crews who had believed themselves secure because of armor thickness were suddenly confronted with penetrations through mantlets, turrets, and hulls. The Flak 88's rounds often punched clean through, igniting fuel or ammunition and causing catastrophic losses. In North Africa and on the Eastern Front, the story repeated itself. Heavy Soviet and British tanks could be neutralized by 88mm rounds at standoff ranges. High velocity also meant a flatter trajectory, which is tactically significant. A flatter shot reduces the need to compute large elevation corrections and reduces flight time, critical when firing at moving targets. This flatter arc made leading targets simpler and increased first shot hit probability. Combine that with accurate optical sights and competent crews, and you have a gun that kills at range more reliably than many contemporaries. For aircraft, the same velocity shortened the time to target and made it much harder for pilots to evade through last-second maneuvers. Engineering improvements across the Flak series continued to push performance. The Flak 36 and 37 introduced refinements in barrel length, recoil absorption, and carriage stability that preserved velocity over longer firing sequences. The later Flak 41 pursued higher chamber pressures and better metallurgy to maintain velocity with heavier, more effective rounds. These evolutionary steps meant the 88 remained relevant even as Allied armor improved. The tactical implication is stark. By delivering projectiles with high kinetic energy at range, the Flak 88 transformed positional or static defenses into lethal sanctuaries. The gun could deny large swathes of terrain to armored maneuver, disrupt offensive tempo, and exact heavy casualties with minimal exposure. Its penetration power didn't simply destroy tanks, it rewired commanders' assumptions about where armor could safely operate. In short, the Flak 88's high muzzle velocity and penetration power converted physics into strategic advantage. Versatility is the single word that most succinctly explains how a piece of equipment can leap from being a specialized tool into a strategic game changer. The Flak 88's designers built a gun optimized for anti-aircraft duties, but a remarkable set of physical and mechanical characteristics. High velocity, flat trajectory, robust carriage, and effective sights meant that it could be repurposed with little modification. Once field commanders recognized this capacity, the 88 became not just an air defense system, but a multi-role platform, anti-aircraft, anti-tank, and field artillery. As an anti-aircraft weapon, the 88 was potent. Its elevation capability and range allowed engagement of high-altitude bombers. Its shells could reach aircraft before they achieved bombing runs, and the velocity minimized lead time. Optical rangefinders and directors improved timing and accuracy, and later radar systems further enhanced aerial target acquisition. The combination of power and accuracy made it a credible deterrent to Allied air offensives in certain sectors. Transitioning to an anti-tank role was almost seamless. The high muzzle velocity and AP/APC rounds that enabled anti-aircraft lethality were equally effective against armor. From 1940 onward, German units began to employ Flak 80s in ground combat, and the weapon quickly acquired a fearsome reputation as a tank killer. It could penetrate heavy armor at standoff ranges, allowing forces with relatively few 88s to dominate defending sectors and hold ground against numerically superior armored formations. Moreover, its flat trajectory simplified fire control when engaging moving land targets, increasing hit probability. As field artillery, the Flak 88 could fire HE shells in indirect roles, delivering destructive effects against positions, fortifications, and formations. This role added an extra tactical layer. A single emplacement could provide immediate direct fire against tanks, switch to anti-aircraft defense if needed, and be tasked to support infantry or suppress enemy artillery via indirect HE fire. Such operational flexibility gave German commanders options. One gun type could fulfill multiple mission profiles, reducing logistical and training burdens while increasing tactical unpredictability for the enemy. Versatility also extended to the tactical levels. The same battery platoon could be sewed across a defensive network, each gun ready to switch roles as the battle demanded. In North Africa, for instance, crews used 80s to fire on advancing tanks, then reoriented to shoot at attacking aircraft supporting the armor. On the Eastern Front, emplacements provided local air defense for supply nodes and simultaneously protected against armored thrusts. This multi-role capability complicated Allied planning, where opposing forces expected to face a specialized anti-tank or anti-aircraft system. They instead encountered a hybrid threat that could change function mid-engagement. This forced the Allies to prepare broader counters, additional artillery, airstrikes, engineer units for clearance, or complex combined arms maneuvers, each of which consumed time and resources. From a logistical viewpoint, deploying one type of gun that could cover multiple battlefield functions simplified supply chains to an extent. One set of crews could be trained on a single platform, ammunition types could be mixed for mission needs, and repair parts were standardized across variants. This efficiency translated into battlefield endurance. Flak batteries could sustain operations longer and adapt to shifting priorities faster than units relying on multiple specialized systems. Ultimately, the 80s versatility turned it into a force multiplier. It was not merely the best anti-aircraft or best anti-tank gun of the early war years. It was the ability to perform both and more that made it uniquely dangerous. A system that can adapt in real time to threats forces the adversary to diversify their approach, creating tactical friction and opening opportunities for exploitation. The Flak 88's multi-role nature therefore magnified its lethality far beyond what raw ballistics alone could explain. Range is a decisive variable in warfare. The ability to strike farther than your opponent changes maneuver, tempo, and survivability. The Flak 88's long effective range, horizontal reach approaching 14 kilometers in anti-aircraft employment, and practical anti-tank engagement ranges of 2 to 4 kilometers, gave German forces a suite of strategic and tactical advantages. These distances placed the 88 outside of the effective return fire of many contemporary tank guns and allowed German crews to engage first from positions of comparative safety. Long range achieved several interlocking effects. First, it enabled standoff engagements. When a gun can destroy an enemy before they can threaten it in return, that gun effectively denies territory to the enemy. Commanders could position 88s to cover approaches, roads, or open ground, and use their reach to create kill zones where armor would be destroyed before it could close to its own effective range. This forced attacking commanders to either avoid these zones, complicating maneuver and often funneling forces into prepared exits, or to invest in suppression and clearing operations. Second, long range multiplied the Flak 88's psychological impact. Knowing that an unseen weapon could strike at multiple kilometers made armor crews cautious. That caution slowed advances, broke cohesion, and often caused troops to bunch or alter routes, which in turn increased vulnerability to mines, artillery, and ambushes. A single well-placed 88 could thus produce an effect that rippled through entire assault plans. Third, range complemented penetration power. Shells fired at 1,000 to 2,000 meters retained substantial kinetic energy and could defeat the armor of many tanks at those distances. Whereas many tank guns in 1940 to 1942 lacked the range or accuracy to engage effectively at those distances, the 88 remained lethal. This ability to engage at standoff distances was particularly effective during the early war campaigns, when many Allied tanks emphasized armor thickness over long-range gunnery. Fourth, long-range amplified tactical flexibility. Within its effective envelope, the 88 could serve as anti-tank, anti-aircraft or field artillery. Artillery doctrine benefited. Commanders could use 80s to hit distant objectives that other immediate artillery could not, applying pressure, disturbing logistics, or shaping the battlefield before direct force contacts. In defensive setups, 80s were frequently integrated with minefields and infantry positions. Their range allowed commanders to cover those obstacles from afar and engage approaching forces long before infantry contact. The geographic impact cannot be overlooked. In open theatres, North Africa's deserts, or the plains of Eastern Europe, visibility and maneuver favoured standoff weapons. The Flak 88 could exploit those conditions to devastating effect. Ambushes in the desert often utilised long lines of sight. 88s sighted on ridgelines or behind dunes could pick off armour columns at distance, then relocate. In the bocage and built environments, 88s were often sighted to cover likely armoured lanes or choke points, applying range to restrict enemy freedom of movement. Operationally, range also affected logistics and prioritization. When a weapon can hold ground at distance, fewer units are needed to defend that ground. That economy of force allowed the German military to mass other assets elsewhere, an important consideration in multi-front conflicts where resources were stretched. In short, the Flak 88's long effective range was not merely a ballistic statistic. It reshaped engagement geometry, slowed enemy operations, created psychological pressure, and offered commanders a tool to control terrain and tempo from a distance. When combined with penetration power and accuracy, range made the 88 a foundational element of German defensive and ambush tactics throughout the war. Firepower is a function of both the power of each round and the number of rounds you can deliver in a given time. The Flak 88 managed an exceptional balance, large high-energy projectiles combined with a sustained and practical rate of fire, roughly 15 to 20 rounds per minute under trained crews. That sustained volume turned individual hits into systemic destruction when called upon. A reliable rate of fire requires mechanical design and human discipline. The 88 featured a semi-automatic vertical sliding breech and an efficient loading cycle that allowed trained crews to maintain cadence without sacrificing accuracy. Crew drills were rigorous. Loaders, rammers, gunners, and spotters each had defined tasks that, when performed in synchrony, reduced reload times and kept the gun in effective action. The cruciform carriage and recoil absorption systems minimized the time needed to reacquire targets after each shot, allowing follow-up rounds to be delivered rapidly. Why does this matter tactically? First, multiple quick rounds on a single vehicle increase the likelihood of catastrophic damage. Tanks often required more than a single penetrative hit to be completely neutralized if ammunition or fuel were not immediately detonated. A quick sequence, 2 or 3 penetration hits, could destroy mobility, kill the crew, and set fires. Additionally, a rapid barrage increases the chance of hitting moving targets through sheer volume, important when enemy vehicles are advancing or maneuvering. Second, rate of fire facilitates suppression. Against infantry and soft targets, the 88's HE rounds could be rained down rapidly, breaking assaults and neutralizing support elements that might otherwise protect armor. In anti-aircraft use, a high cyclic rate shortens the window for aircraft to pass through effective fire zones without being hit, increasing the probability of lethal strikes during brief passes. Third, rapid firing amplifies ambush tactics. A hidden 88 that opens with a rapid series of rounds can disable multiple vehicles in a column before they can effectively return fire or coordinate a response. In practice, this allowed relatively small flak detachments to achieve disproportionate results, neutralizing armored spearheads and inflicting rapid casualties that paralyzed units. Training and doctrine are vital to sustaining rate of fire. German crews drilled extensively. Their training emphasized not just speed, but safe, coordinated operations under pressure. Ammunition supply discipline, keeping belts, racks, and transfer procedures orderly, prevented jams and reduced reload delays. The weapon's reliability in adverse conditions also meant that rate of fire could be maintained in environments, dusty deserts, freezing tundra, where lesser systems would falter. Engineering improvements in successive models also supported sustained firing. Better recoil systems, improved cooling concepts, and more robust carriage designs reduced wear and permitted longer firing sessions without degrading accuracy. This meant the gun could be used intensively during critical battle windows, delivering concentrated fire when it mattered most. The psychological effect of a rapid, pounding barrage should not be underestimated either. For crews under fire, hearing the staccato rhythm of a heavy gun and feeling the shock of nearby impacts reduces morale and degrades coordination. The combination of heavy, penetrating hits and the noise and concussion of rapid rounds added a sensory dimension to the gun's lethality. In sum, the Flak 88's high rate of fire magnified its destructive potential. It transformed the weapon from one that could deliver occasional potent strikes into a platform capable of sustained, multi-target lethality. Pair that with accuracy, range, and penetration, and the operational result was a versatile and devastating system capable of changing the course of engagements through concentrated, timely fire. Mobility and the capacity to deploy rapidly are force multipliers on the battlefield. Despite the Flak 88's mass and size, designers and tacticians made mobility central to its practical employment. The gun's carriage could be towed and emplaced with reasonable speed, and elements such as detachable wheels and collapsible supports facilitated quicker moves and assembly. It was heavy but not immobile, and that nuance mattered. A heavy gun that can be moved is more dangerous than a light weapon that cannot. The 80's mobility enabled several tactical patterns. First, ambush and shoot and scoot tactics. In open terrain, most dramatically in North Africa, positions could be prepared such that the gun fired from concealment at approaching armour, then was towed to a secondary position to avoid counter-battery or direct assault. That fluidity allowed German forces to exploit the weapon's strengths, range and penetration, while minimizing its exposure to concentrated counterattack. Second, mobility permitted tactical concentration. Commanders could mass a few guns to critical points, choke points, bridges, road intersections, creating local areas of denial that influenced enemy planning. Mobile deployment also allowed repositioning in response to breakthroughs, enabling the 88 to provide reinforcing anti-tank or anti-aircraft coverage where it was most urgently needed. Third, strategic redeployment was practical. Flak 88 units were moved between theatres, North Africa, Italy, the Eastern Front, and Western Europe, because they could be disassembled, loaded, and transported. This capacity to shift heavy firepower across fronts gave German high command flexibility in allocating limited resources. It also meant that lessons learned in one theatre could be applied elsewhere. Tactics of camouflage desert ambush translated to hedgerow and urban setups in Western Europe. Concealment techniques amplified mobility's effect. Crews learned to hide guns under camouflage netting, in ruined buildings, behind embankments, or in foliage. The 88's power meant it did not need to be on a forward ridge to be effective. A well-hidden gun in a defilade could fire and remain difficult to locate. Effective camouflage extended the weapon's lethal window by reducing detection and counter-battery accuracy. Logistics and support elements were part of the mobility equation. Towing vehicles, spare parts, and trained crews moved with the guns. Engineers prepared firing pits, and infantry screens provided local security. The 88's mobility network mirrored a small mechanized organization, enabling it to function as a semi-autonomous anti-armor or anti-aircraft cell. Terrain influenced deployment styles. In the desert, long lines of sight favored sighting guns on ridgelines or behind dunes where they could see columns at distance. In the bocage of Normandy, guns were concealed to cover lanes and junctions, often with prepared hides and firing apertures. In urban or fortified zones, guns found niches in strongpoints where they could interdict armor and provide local air defense, often to dramatic effect. The tactical fallout was significant. Mobility made the 88 unpredictable and resilient. Commanders could not rely on destroying a single emplacement to negate a sector. Secondary positions and mobile redeployment meant the threat persisted. Combined with accurate reconnaissance and good command control, the Flak 88's mobility allowed it to shape enemy options, delay offensives, and provide a stabilizing defensive effect disproportionate to the number of guns present. In short, the Flak 88's mobility converted raw firepower into operational influence. The ability to move, hide, shoot, and move again made it a persistent and elusive threat, letting relatively small numbers of guns exert outsized control over battlefield tempo and maneuver. A lethal gun requires not only destructive rounds, but the ability to find, track, and hit targets consistently. This is where sighting and fire control play decisive roles. The Flak 88 benefited from advanced optical directors, rangefinders, and eventually radar integration, making it more than a big gun. It was a precision system. Accurate targeting increased first-shot hit probability and allowed crews to exploit both long-range and high-velocity. Optical systems formed the backbone early in the war. Telescopic sights, mechanical directors, and optical rangefinders allowed crews to estimate distance, compute lead, and adjust for elevation. Against aircraft, these directors coordinated barrages by translating range, altitude, and speed into firing solutions. Against ground targets, optical calculation simplified lead and elevation corrections, allowing crews to exploit the 88's flat trajectory and high velocity with clinical accuracy. Training amplified the hardware's effectiveness. German gunners were trained in synchronized procedures. Spotters used binoculars and rangefinders to call out data. Calculators and firing tables turned those numbers into azimuth and elevation settings. The gunner aimed while loaders sustained cadence. That procedural discipline made the Flak 88 a dependable long-range precision weapon, not merely a brute-force cannon. Radar's eventual integration advanced capabilities significantly. Early German radar systems, primitive by modern standards but cutting-edge for the period, provided early warning and trajectory calculation for high-altitude aircraft. Radar allowed the gun to engage fast, high-flying targets by predicting their path and cueing the optical directors. While not all batteries received radar due to production limits and changing fronts, those that did saw marked increases in aerial engagement success. For anti-tank roles, sighting sophistication translated directly into survivability benefits. Accurate range estimation reduced wasted shots and permitted crews to exploit first strike advantages. A single well-aimed 88 at 1,500 to 2,000 meters could neutralize a tank without allowing it to close. Fire control allowed the gun to engage moving targets in relative darkness or poor visibility by combining pre-surveyed firing sectors with observed fall of shot adjustments. Fire control also facilitated coordinated battery operations. Multiple guns could be networked to deliver intersecting fire or to rapidly adjust to a moving formation. Using observers, telephone lines, and pre-mapped firing tables, flak batteries could mass fire on a sector or switch targets seamlessly. That systemization turned individual guns into a combined weapon system. On the logistics side, accurate fire control reduced ammunition wastage and improved effectiveness per shell expended, crucial in campaigns where supply lines were stressed. Maintenance of sights, calibration tables, and crew drills ensured these advantages persisted. Crews who mastered fire control delivered far greater battlefield impact than those who relied on volume alone. In practice, the Flak 88's fire control suite allowed German forces to win the first shot battle. Whether against armor or aircraft, accurate rapid engagement increased kill probability and reduced exposure. That precision turned an already powerful gun into a consistent battlefield arbitrator, capable of reliably undermining enemy plans and protecting critical assets. Weapons have physical and psychological effects. The Flak 88 delivered both, and often the psychological dimension amplified the tangible one. The gun's reputation became a force multiplier. Fear altered behavior, slowed aggression, and forced tactical conservatism. Commanders and crews who feared the 88 often paid an operational price in time, cohesion, and initiative. The first psychological effect stemmed from unseen lethality. An 88 could sit concealed, then open fire at long ranges where enemy guns could not effectively reply. Crews that had once considered themselves secure suddenly faced a threat that could kill from beyond return fire distance. That perceived invulnerability eroded morale and made commanders cautious. Units approached potential 88 covered zones with additional reconnaissance, supporting fires, or engineer teams, all actions that cost time and reduced momentum. Second, the gun's dual-role ambiguity increased stress. Opposing forces could not always tell whether a given emplacement targeted air or ground threats. This uncertainty exacerbated fear. Tank crews had to wonder whether a post might be an anti-tank sniper or an air defense battery, leading to slower advances and more conservative maneuvers. The unknown is often as paralyzing as the known. Third, sensory shock played its part. The heavy concussion, bright muzzle flashes at night, and catastrophic secondary detonations when tanks were penetrated left vivid impressions on survivors. This visceral experience spread quickly through units as word of the 80's destructive efficiency circulated. Stories of entire companies halted, vehicles immobilized, and crews killed by a single well-placed hit became casualty lore, reinforcing caution. Fourth, the requirement to alter tactics to neutralize the 88, calling artillery, airstrikes, or engineer clearing, imposed cognitive load on commanders. Rapid decision-making under these stresses often led to mistakes. Diverting supporting arms to suppress flak batteries offered the Germans windows to exploit elsewhere, such as conducting counterattacks or reinforcing other defense axes. Fifth, the political and strategic psychological effects were non-trivial. Local battlefield successes using the 88 fed broader narratives of battlefield superiority. Allied commanders analysing losses had to weigh the presence of 80s when planning operations, sometimes leading to postponement or rerouting of offensive efforts. The necessity to deal with 88 emplacements added friction to planning cycles and consumed scarce air or artillery resources. Finally, the psychological effect extended to logistics and morale longer term. Repeated shocks to armour units reduced training confidence and forced adaptations in crew behaviour. More conservative engagement ranges, reliance on infantry screens, and increased use of deception or reconnaissance. Each adaptation was effective but costly in tempo and initiative. Thus, the Flak 88's reputation functioned as an intangible weapon. It changed how enemies thought and acted. In war, altering an opponent's perception and behaviour is often as valuable as destroying material. The 88 achieved both outcomes, making its psychological impact a central contributor to its overall lethality. A weapon's battlefield potency depends on its engineering quality and adaptability, areas where the Flak 88 excelled. Precision metallurgy, careful machining, and a modular approach to upgrades produced a system that was reliable, maintainable, and improvable across different war phases. The German industrial approach favoured high tolerances and robust components, resulting in a gun that could be fired intensively and still hold zero, a remarkable trait in prolonged campaigns. Reliability manifested across theatres. In North Africa, gritty sand and heat could disable less well-built mechanisms, but the 80s continued to perform. On the Eastern Front, extreme cold tested lubricants, seals, and metal properties. The gun's engineering handled these stresses better than many contemporaries. That resilience meant crews did not need frequent workshop periods, maintaining high operational availability even under attritional conditions. The Flak series demonstrated a deliberate upgrade path. The Flak 18 established the baseline. The Flak 36 added carriage and recoil improvements. The Flak 37 improved fire control integration. And the Flak 41 pushed muzzle velocity and chamber design. These incremental changes addressed battlefield feedback, mobility, rate of fire, and maintainability were all targets for improvement. Importantly, upgrades were often retrofit-friendly. Barrels, recoil units, and carriages could be swapped or enhanced without discarding whole systems. Spare parts and repair doctrines were part of the engineering success. Field units carried spares and maintained disciplined maintenance cycles. Crews were trained not just to operate, but to perform routine repairs and adjustments, allowing a damaged gun to return to service quickly. That repairability mattered in contested supply environments where manufacturing throughput could not keep pace with losses. Manufacturing consistency contributed to predictability in performance. Tight quality control meant each gun behaved similarly, vital for fire tables and sight calibrations. When fire control relies on known ballistic coefficients and consistent barrel wear, the advantages in accuracy are tangible. Allied pieces with more variability in some cases could not always match that predictability under similar conditions. Engineering prudence extended to crew ergonomics and servicing. Loading procedures, shell handling, and maintenance points were designed to reduce fatigue and speed servicing. Those human-centric design elements meant crews could sustain rates of fire longer and with fewer accidents. Economic constraints later in the war forced compromises, and not all late-war Flak 80s matched early production quality. Nonetheless, the core engineering resilience and modular upgrade structure preserved the gun's battlefield utility. The capacity to sustain operations under different environmental stresses, combined with field repairability and upgrade paths, ensured the 88 remained combat effective as the conflict evolved. In sum, engineering excellence, material quality, modular upgradability, repairability, and manufacturing consistency underpinned the Flak 88's practical lethality. A powerful weapon that is unreliable is useless. The Flak 88 paired firepower with dependability, a combination that prolonged its effectiveness across multiple fronts and years.